Good morning. We will start with wave impedance. Electromagnetic wave can propagate along three independent directions at a point. That means electromagnetic wave can propagate either along the x, y or z. Hence there will be 6 field components for electric field and magnetic field in general. So wave impedance can be defined as a ratio of transverse component of electric field to the transverse component of magnetic field. That means suppose electromagnetic wave is propagating along the z-axis, then the transverse component of electromagnetic wave is either its x component or its y component. So you can define wave impedance as z is equal to Ex by Hx or Ey by Hy. So the wave impedance as viewed from the positive z-axis is denoted by ZZ. This small z, that is the subscript z, represents the direction, okay, and is also denoted by z plus xy. This xy represents the transverse component, okay. Now the wave impedance for electromagnetic wave in its transverse mode is defined as eta into square root of 1 minus omega c by omega the whole square, where eta is the intrinsic impedance of the dielectric medium given by the formula square root of mu by epsilon, which we have already studied in our second module. And here you can see when this omega c, when the cutoff frequency is 0, what happens to z? It is equal to eta. Similarly, the wave impedance for transverse electric mode is given by eta divided by square root of 1 minus omega c by omega the whole square, and these two are the expression for wave impedance in TM mode and TE mode. Next is the attenuation factor. Now the electromagnetic wave propagating through a waveguide will suffer attenuation to a certain extent. It suffers attenuation mainly due to the dielectric medium and due to the imperfectly conducting guided walls. So you know, here you can see the structure of a rectangular waveguide. The darkened portion represents the wall of the conducting medium, and the portion between this, in between the wall, represents the dielectric medium. So the attenuation is mainly caused due to the imperfect conduction of this conducting wall and due to the losses in this dielectric medium. Okay, that is written here. A rectangular waveguide supports TM and TE mode, but not TEM mode. Now here you are coming across a new term TEM, which is known as transverse electric magnetic mode. Okay. In transverse magnetic mode, you know what Hz is equal to 0, and transverse electric mode, you know Ez is equal to 0. And in transverse electric magnetic mode, Hz and Ez will be equal to 0, which is not supported by a rectangular waveguide, while TEM mode is supported by a parallel waveguide. Attenuation of these propagating modes results when there are losses in the dielectric and in the imperfectly conducting guided walls. Okay. The attenuation constant due to the losses in the dielectric medium is given by the formula alpha d is equal to sigma square root of mu by epsilon by 2 square root of 1 minus fc by f, where mu and epsilon, you know, it is a permeability and permittivity of the dielectric medium, because here we are dealing with the losses due to the dielectric medium between the conducting walls, and sigma is the conductivity of the dielectric medium, and alpha d represents the losses in the dielectric medium. The second factor that contributes to the attenuation of electromagnetic wave through a waveguide is due to the losses in the walls of the dielectric. You know, this wall, actually the wall means it is the wall of our conducting medium, which is in contact with the dielectric medium. So since the wall, I already told you that in a rectangular waveguide the walls are conducting while the inner surface are not conducting. So Thus conducting walls are in contact with the inner surface, which is a dielectric medium. So in some cases there may be imperfect conduction of the walls, and the loss due to the imperfect conduction of the walls is given by alpha W is equal to Rs by B square root of mu epsilon into square root of 1 minus Fc by F into 1 plus 2B by A Fc by F the whole square, where A and B are the length and breadth of the rectangular waveguide, Fc the cutoff frequency, and F the frequency of the electromagnetic wave, and one new term which you are coming across is Rs, which Rs is known as surface resistance of the wall material, which is given by the formula square root of omega mu by 2 sigma. And next is group velocity. Group velocity is defined as a speed at which the information travels, and it is given by Bg is equal to C into square root of 1 minus Fc by F the whole square, which is given by 1 by square root of mu epsilon square root of into square root of 1 minus Fc by F the whole square. And that's all in this slide, and thank you.